Okay, more on parallel plate capacitors, but I forgot to mention in this video, or at least draw in this video, that if we have a bunch of positive charge here and a bunch of negative charge here, it's going to create an electric field here. So that's where our potential difference would come from. So there would be some voltage here, we could say V naught, and this could be V final, and there's going to be a change in voltage, which is V final minus V naught, because there's an electric field going downward. So I just wanted to draw that out more explicitly. On to more about parallel plate capacitors and the physical properties that make them up and define a farad. So here are my parallel plate capacitors, and I want to define this here. This surface I will call A, which is also this surface here. Let's hook this up to a battery. Why don't we? So this is a voltage source, and we'll get a bunch of positive charges on this plate and a bunch of negative charges down here. Okay, and all of this is separated by a distance d. Okay, what would happen if the parallel plate capacitor had a larger area? Well, that would mean that there would be more charges that could stick to these plates, and if we had more charges, then we have a larger E field. There's this E field that's going down. So if I increase A, then the capacitor can store more charge. If A is larger, capacitor can store more charge. And if that's the case, well then C is larger. The capacitance must be larger if A is larger. So there must be a proportional relationship between the capacitance and the area of a capacitor. What about if I increase this distance? Well, if D is larger, the distance between the parallel plate capacitors, then the E field decreases because my charges are getting further and further away. And if that's the case, then the capacity to store charge also must decrease. So my relationship here then is that the capacitance must be proportional to 1 over the distance. So let's put all of this together. The capacitance relationship must rely on A being in the numerator, D being on the denominator. If we test this out, we find some constant E naught, which will define E naught to be the permittivity of free space. And this E naught constant is 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. Okay, so suppose that we fully charge up this capacitor. We leave the battery on for a given amount of time. We build up some positive charge. We build up some negative charge. We'll say that this is positive Q, negative Q. And I want to know if this is fully charged and I cut one of these wires here. Then say I move the capacitor closer so D decreases, what happens to the capacitor itself? Wires cut, capacitor is moved closer, still not touching, just move closer so D decreases. What happens then? Well, the charges on the capacitor would stay the same. They're not going to flow because the wire is cut. So Q stays the same. But what does change? Well, the capacitance must increase because D is decreasing, causing C to increase. And that must cause the voltage to decrease, or the voltage difference to decrease between the plates. New scenario. Say I'm fully charged, and now I keep the wires connected, so no longer are they cut. I just move the plates closer. What happens? In this case, because the battery is still hooked up, V stays the same. But what changes? Well, once again, the capacitance must increase because I'm moving the plates closer, causing the charge that's built up to also increase. So I'm getting more charges on the positive and negative side because I get these things closer. And the same could be said for the area. I can make the same area changes if I cut the wires or if I keep the battery connected and just move them closer. And I would see something similar. At least I could say that Q is the same if the wires are cut, and B is the same if the battery is always connected, and then see what happens from there. Okay, that's all I wanted to say for now on parallel plate capacitors. With that, let me make sure that you can see everything. With that, I will see you guys soon.